Sound. Sound has power. Sound has appeal. Sound can be used to see the invisible. And we use sound to communicate. It's part of being human. So, what is sound? Sound is vibration, a shaking to and fro. Generally, we talk about sound travelling through the air. The air vibrates with little waves of pressure moving through it. But waves of pressure, and therefore sound, can travel through any substance. And of course, the flip side to this is that sound will not travel through empty space. In the vacuum of space, for example, there is no substance to vibrate. Astronauts' voices are transmitted across space by radio, not sound. Sound is a mechanical vibration and can only travel through solids, liquids, and gases. To help understand sound waves, it's worth watching waves in water, because waves of any kind behave much the same. For example, you can have lots of little short waves or fewer longer waves. Where two sets of waves cross, they can pass through each other without stopping. And they reflect off any place where the medium, in this case water, ends. If an obstacle is small compared to the waves, there's very little reflection. The wave bends around and goes on. Longer waves lose their energy slower than shorter waves and therefore travel further. And when something goes faster through the water than wave speed, it leaves behind a V-shaped pile of waves. But let's make it clear that despite many similarities, these waves are not sound waves. They're just surface waves. They go up and down at right angles to their travel, and they go very slowly compared to sound. Sound is waves of pressure lined up with the direction of travel, and it goes quite fast right through things, not just on the surface. For example, sound travels right through the body of the sea. How can sound do that? Well, it's because all substances have a slight springy quality. Here's a direct pressure wave travelling along this spring. The spring doesn't move up and down. Instead, waves of compression and the corresponding expansions travel along it. All substances have the ability to act like a spring. The molecules of even quite rigid substances can be pushed a tiny bit closer together, allowing a little compression. For example, a chunk of rock may hardly look like a spring, but the graph shows that it compresses without breaking ever so slightly before it can't take any more. So something even as hard as rock acts like a very tough spring, and that means it will carry a sound wave. In fact, the less compressible a substance is, the faster it can carry a sound wave. But on the other hand, heaviness, that is, high density, slows it down. So the actual speed of sound in a medium is a trade-off between what is called the medium's elasticity and its density. For example, rocks and metal are inelastic, like very strong springs. That's a fast factor. But they're also heavy and quite dense, and that's a slow factor. The trade-off results in a speed of around 5,000 metres per second in a substance such as steel. Now, air is 1,000,000 times more elastic than steel, so you might expect sound to go 1,000,000 times slower in air. But it's also less dense and easier to move, so the speed isn't reduced as drastically as you might think. It's about 340 metres per second in air, about 15 times less. Knowing the speed of sound allows us to use it to measure distance. The time between the lightning and the thunder is a well-known way to estimate the distance to the storm. At 340 metres per second in air, sound goes about 1 kilometre every 3 seconds. So this thunderstorm is about 4 kilometres away. Here's a more sophisticated use of timing the speed of sound. The handpiece puts out pulses of sound that are ultrasonic, that is, above the range of human hearing. Between the pulses, it catches and measures the time of the echoes. Remember that, like all waves, sound waves reflect off boundaries, in this case, the edges of the baby in the womb. The echoes are translated into electrical pulses, projected onto a screen, and lo and behold, a picture is drawn. Using a screen to display sound is a good way of understanding it. Here's a very low-pitched sound, in fact so low you can't hear it. You could imagine this dot as a molecule of a substance vibrating with the sound. As we raise the sound frequency, the dot soon vibrates so fast that it just leaves a line on the screen, and still we can't hear the sound. We'll have to raise the frequency even more to hear it. To see it better, we'll draw the dot out across the screen. There. But remember that this sideways stretch is introduced just so that we can see what's going on. Sound waves don't move sideways. Now let's raise the frequency to hear the sound. See how the rate of vibration increases? It's a pure sound, so the waves are nice and smooth. Smooth waves are characteristic of music, which creates recognisable patterns of waves. Recognisable to our ears, that is. All musical instruments are made to produce sound in neat ratios. Most obvious to the ear is a doubling of the sound frequency, and in Western music this is divided into a basic scale of 8 notes, called an octave. To double the frequency, you halve the wavelength. So if you played on one string, the octave is found halfway up the string. By adding different shaped sound waves from different instruments and mixtures of frequencies and rhythms, music creates something very attractive out of vibrations in the air. By contrast with music, a voice is a more messy collection of sound waves, if you see what I mean. And when we get a load of random rubbish with no pattern at all, that's noise. But now let's go back to a pure note and take the frequency up and up and up until we can no longer hear the sound. The screen now shows 16,000 vibrations per second. The sound is still coming out your loudspeaker right now, but will be inaudible to most people. So sounds do exist which are ultrasonic, higher than the range of human hearing. Many creatures have the ability to hear ultrasonic sounds, and a few, living in environments where vision is limited, actually transmit and listen to these high frequencies, as did the ultrasound machine, to get a sound image of the world around them. But why ultrasound? Why not ordinary sound? Well, it's mainly because very high frequencies mean many waves packed close together. In other words, a very short wavelength. It takes short wavelengths to detect small objects. We can learn a great deal from the world of sound beyond our hearing. At the opposite extreme are sound waves so low in frequency that we don't hear them, we feel them. Earthquakes are enormous, very low frequency sound waves. Because these wavelengths are very long, whole buildings can be vibrated as entire objects. Because these waves are so potentially devastating, the detection and study of earthquakes is a well-established branch of science called seismology. Ed Paul is a seismologist with the Australian Geological Survey Organisation working at Mundaring in Western Australia.
This map shows the distribution of earthquakes around the world, and as you can see, they are concentrated in certain zones. These zones mark the edges of the tectonic plates which make up the surface of the Earth. Australia sits within one of these plates, and the level of activity is much lower. But this doesn't mean we can afford to ignore earthquakes, because the earthquakes are actually quite shallow and therefore close to the surface, and they can still do a lot of damage.
For example, this was Newcastle, New South Wales in 1989. 12 people were killed. We can't accurately predict earthquakes yet, but what scientists can do is to locate them and study them so that they can identify the high-risk areas.
To detect earthquakes, we use an instrument like this called a seismometer. This one has a heavy magnet suspended by leaf springs over a coil. When the ground shakes due to the passage of an earthquake shock wave, the coil, which is attached to the frame, moves, but the magnet tends to stay still. This movement of a coil in a magnetic field induces a small electrical signal which can be amplified and recorded and displayed. What we have here is a recording of a recent local earthquake. The first shock wave to arrive is called the P wave. It is a longitudinal or pressure wave and is really a sound wave travelling through rock. It travels at about 10 kilometres per second. The second wave to arrive is called an S wave. This is a transverse or shear wave with particle motion from side to side. It travels at about half the speed of the P wave. They in turn may be followed by surface waves, which travel slower still, just like waves on water. Obviously, if you're being shaken by an earthquake, you're not going to be checking which kind of wave is shaking you. But there are three possible kinds of waves, and the timing between them gives the distance to the quake. If you have the distance from 3 or more stations, then the earthquake can be located by triangulation. Now we have a network of seismographs across Australia. As a shock wave comes through, we can see the order in which the stations detect it. This gives the direction from which the earthquake comes, and if we also know the distance, then this gives us another method of locating earthquakes.
The ultimate aim of seismology is to accurately predict earthquakes. We can't do that yet. That ability will no doubt come from learning to understand even better the vibrations of the Earth. It's another challenge in the science of sound.